Among the stars, a rare kind burns brighter, hotter, and larger than almost any other, the blue giants. These cosmic titans live fast and die young, shaping galaxies in their wake. Today we'll uncover the science behind these dazzling stars. If you enjoy this journey, please like, subscribe, and share. Thank you for watching. Now let's begin. In the cold reaches of galaxies far from the heat of nearby stars, there exist vast clouds of gas and dust. These regions are called molecular clouds because most of the hydrogen within them is bound into molecules. They're not uniform. They contain knots and filaments where density varies from place to place. Gravity acts most strongly where density is highest, slowly pulling gas inward. Over time, certain clumps within a molecular cloud become unstable under their own weight. When that happens, contraction begins. The gas does not fall directly inward as a whole, but compresses, gradually releasing energy in the form of heat as particles collide more frequently. Inside a large molecular cloud, many such sites of collapse can occur, producing groups of stars that eventually shine together. Among these newborn stars, only a few will become blue giants, because only a fraction of clumps are massive enough to sustain the conditions that lead to their formation. The first stage of collapse is subtle and quiet when viewed across astronomical timescales. For hundreds of thousands of years, gas continues to gather, forming a dense core. Dust within the cloud shields this region from much of the outside starlight, keeping it cool enough for collapse to continue. As density increases, the central temperature rises. At first, this heating does not reach levels high enough for nuclear reactions. Instead, it marks the protostar stage when the object is still surrounded by a thick envelope of gas. Material falls inward from the envelope onto the growing star, adding to its mass and driving further compression. In some cases, disks of material form around the protostar shaped by rotation. These disks can give rise to additional stars in close proximity, or even to planets much later, though in the case of blue giants, their lives are too short for planetary systems to settle into long-term stability. The decisive factor in whether a forming star becomes a blue giant lies in the amount of mass gathered during this stage. If a clump accumulates only a few times the mass of the Sun, the resulting star will shine for billions of years as a smaller, cooler type. But if the collapsing region gathers more than about 10 times the Sun's mass, the internal conditions move along a very different path. Gravity squeezes the core far more strongly, producing central temperatures that rise with great speed. Above this threshold, the protostar begins to approach the defining conditions of a blue giant. Its surface will eventually become extremely hot, and its energy output will far exceed that of average stars. During the late protostar phase, radiation pressure begins to build. Radiation pressure is the force exerted by light itself as photons carry momentum and push against matter. In lower mass stars, radiation pressure is not strong enough to play a major role, but in very massive protostars it becomes significant. Even before nuclear fusion ignites in the core, light streaming outward begins to oppose the inflow of gas. This interaction can limit how much more material the star can gather from its surroundings. In practice, this sets an upper boundary on stellar masses, though the exact limit remains uncertain and depends on local conditions such as metallicity, which is the proportion of elements heavier than hydrogen and helium present in the gas. Eventually, central temperatures surpass the critical point where hydrogen nuclei can fuse into helium. At this ignition moment, the protostar becomes a true star, beginning its life on the main sequence. For blue giants, fusion proceeds differently than in stars like the Sun. While the Sun primarily fuses hydrogen through the proton-proton chain, a blue giant's higher temperature favors the carbon-nitrogen-oxygen cycle, where hydrogen is fused into helium using carbon-nitrogen and oxygen nuclei as catalysts. This cycle requires higher temperatures, but releases energy more efficiently in such massive stars. The balance between gravity pulling inward and fusion energy pushing outward is established, marking the start of the stable main sequence phase. From outside, the emergence of a blue giant transforms the surrounding cloud. The star's intense ultraviolet radiation begins to ionize hydrogen in nearby gas, producing glowing regions known as H2 regions. These appear as vast, faintly luminous clouds with sharp edges where the ionizing photons no longer reach. The pressure of ionized gas pushes outward, disrupting the molecular cloud from which the star was born. In this way, the birth of a blue giant can shut down further star formation nearby by dispersing the very material that might have formed other stars. In clustered environments, this effect can shape the development of entire stellar nurseries, producing clearings and cavities around the hottest stars. Though the collapse of a molecular cloud fragment is a natural outcome of gravity, the details of how massive stars form remain an area of active research. One key uncertainty is how radiation pressure interacts with infalling material. In simple models, radiation should halt accretion once a protostar reaches a certain mass, preventing the formation of very massive stars altogether. Yet observations show stars dozens of times more massive than the Sun do exist. This suggests that processes such as disk accretion, where gas falls inward along narrow channels or turbulent flows within the cloud, allow material to reach the forming star despite intense radiation. In some cases, mergers between protostars may contribute, though this is still debated. As a result, each blue giant represents the successful crossing of many thresholds. Enough mass had to be gathered despite the outward push of radiation. Collapse had to continue without fragmentation breaking the cloud into smaller stars. The final product is an object with mass high enough to ignite fusion at enormous rates. These conditions are rare compared with the formation of smaller stars. For every blue giant that forms, many hundreds of lower mass stars appear in the same region. This rarity explains why blue giants, though visually dominant in young clusters, are numerically a small fraction of all stars. The early lives of these massive stars are short compared with the cosmic timescale. While they stabilize as main sequence stars for a brief period, their birth signatures remain visible. Many still sit within the cavities carved into their parent clouds. The contrast between their bright blue-white light and the dim red glow of ionized gas makes them stand out against their backgrounds. Observations from telescopes sensitive to multiple wavelengths reveal the full impact wind shocks and glowing shells all surrounding the young stars. Thus, the story of a blue giant begins not with a sudden burst, but with the quiet, persistent work of gravity, drawing gas into denser forms, gradually leading to ignition, and finally to the brilliant presence that defines its category. The formation of stars of all sizes depends on the amount of material gathered during collapse, but in the case of blue giants, the requirement is especially strict. Mass is the single most important factor that determines a star's eventual classification structure and lifespan. When a protostar forms within a molecular cloud, the balance between what is available and what can be accreted sets the course of its life. For a star to reach the conditions of a blue giant, it must accumulate at least 10 times the mass of the Sun, and often far more. This requirement is not arbitrary. It is dictated by the laws of physics that govern the interplay of gravity, temperature, and pressure inside the collapsing core. The pressure at the center of a forming star rises with its mass. In smaller stars, the central pressure reaches values sufficient to initiate hydrogen fusion only through the proton-proton chain which dominates in lower temperatures. In stars with much greater mass, the central temperature climbs higher, activating the carbon-nitrogen-oxygen cycle as the primary mechanism of energy generation. This cycle demands greater temperatures but allows fusion to proceed at far more rapid rates. Therefore, mass is not only a measure of how much material the star contains, it is also the factor that defines which nuclear processes dominate within it and how quickly they run. The consequence of this requirement is that blue giants are rare compared with smaller stars. The initial mass function, which describes the statistical distribution of stellar masses formed in galaxies, shows that nature favors the creation of many small stars and very few large ones. For every massive star formed, hundreds of low-mass stars emerge in the same stellar nursery. This is partly due to the way gas fragments during collapse. The same gravitational instability that allows large cores to form also promotes the splitting of clouds into many smaller clumps. Only in regions where conditions are especially favorable do cores large enough to form blue giants survive and grow. Once a protostar has passed the threshold of mass necessary for a blue giant, its evolution follows a different trajectory than that of smaller stars. High mass not only influences fusion, but also affects luminosity. The relationship between mass and luminosity in main sequence stars is steep. While the sun shines with a certain steady brightness, a star 10 times more massive shines, thousands of times brighter, and a star 20 times more massive can outshine the sun by tens of thousands of times. This is because greater mass compresses the core to higher pressures, which accelerates fusion rates dramatically. The star therefore releases far more energy at its surface, appearing intensely luminous. This steep scaling means that adding a relatively small amount of additional mass can transform a star into a dramatically different object. A star just below the threshold may appear as a mid-type star with billions of years of stable fusion ahead. A star just above the threshold ignites as a blue giant, burning its fuel rapidly and living only a few million years before undergoing significant changes. Thus, mass sets not only the classification but also the timescale on which the star evolves. The requirement for high mass also explains why blue giants are found preferentially in certain environments. They appear most often in dense star-forming regions where there is enough raw material to form them. Smaller clouds are unlikely to produce stars above the threshold because the available gas will fragment into many lower mass stars. Large molecular complexes, such as those in spiral arms of galaxies, provide the conditions necessary to assemble massive cores that eventually give rise to blue giants. Observations confirm that clusters rich in blue giants almost always trace areas of recent star formation. Because of their mass requirements, blue giants are often born alongside many companions. They frequently appear in clusters or associations rather than in isolation. This further emphasizes the role of mass. The collective collapse of a cloud allows many stars to form simultaneously, but only a few gather enough material to exceed the necessary threshold. The presence of these massive stars then influences the rest of the cluster through intense radiation and powerful winds. Thus, the requirement for mass not only shapes the star itself, but also its environment. A second consequence of high mass is the instability it introduces. With greater mass, gravity pulls more strongly inward, but the rate of fusion produces a stronger outward push of radiation. This balance is inherently more delicate in massive stars. Small fluctuations in the rate of fusion can have significant effects on the star's outer layers. For this reason, many blue giants show variability in brightness and spectral lines. Their large mass allows them to shine brilliantly, but it also pushes them closer to physical limits where stability is harder to maintain. The precise upper limit of stellar mass remains uncertain. Theoretical models suggest that radiation pressure should halt the growth of stars above a few dozen solar masses, yet observations reveal stars with masses over 100 times that of the Sun. This discrepancy highlights ongoing questions about how masses accreted in extreme conditions. Some explanations propose that accretion occurs through disks where gas falls inward in streams shielded from radiation. Others suggest that massive stars can form through the merger of several smaller protostars within crowded clusters. Whatever the process, the fact remains that enormous stars do exist, and many of them manifest as blue giants or blue supergiants. When astronomers examine star-forming regions, they often measure the distribution of masses to compare with theoretical predictions. The observed initial mass function is remarkably consistent across different environments, but the upper end where blue giants reside shows more variation. This indicates that while the broad tendency to form many small stars is universal, the exact conditions that produce very massive stars may differ from region to region. This is another area of active study as it influences not only the understanding of star formation, but also the chemical evolution of galaxies. The requirement of high mass has a direct bearing on the lives of galaxies as well. Blue giants are short-lived, but during their existence they produce vast amounts of energy and drive powerful winds. Later, many of them explode as supernovae, enriching their surroundings with heavier elements. Because only high-mass stars follow this path, the frequency of blue giants affects how galaxies evolve chemically over time. Their rarity means their contribution is specialized but critical. The clarity with which mass dictates the fate of stars provides astronomers with a framework for classification. By measuring surface temperature, luminosity, and spectra, the approximate mass of a star can be inferred, and with that its lifetime can be estimated. For blue giants, the conclusion is always the same: they are massive, luminous, and short-lived compared with most stars. Their defining requirement is that they crossed a threshold at birth that most stars never approach, gathering enough material to ignite fusion under extreme conditions and to shine with extraordinary brightness for only a brief span. When a blue giant has fully ignited hydrogen fusion in its core, it takes its place on the Hertzsprung-Russell diagram, which is a plot used by astronomers to classify stars according to their luminosity and surface temperature. This diagram arranges stars so that hotter stars appear on the left and cooler stars appear on the right, while brighter stars are shown higher up and dimmer stars lower down. The Sun, for example, sits near the middle of the main sequence, which is the diagonal band where stars spend most of their lifetimes steadily fusing hydrogen into helium. Blue giants, however, occupy a very different part of this diagram. They are found in the upper left region, where stars are both extremely hot and extremely luminous. Their position on the diagram is not arbitrary. It reflects the physical relationship between mass, luminosity, and temperature. The higher the mass, the higher the core pressure and temperature. That in turn leads to greater fusion rates and higher energy output. The outer layers of the star respond by reaching very high surface temperatures, which produce the blue-white colour observed from Earth. The result is that these stars shine tens of thousands to hundreds of thousands of times brighter than the Sun, while maintaining surface temperatures above 20,000 degrees Kelvin. This combination of brightness and heat fixes their location on the diagram in a region that few stars ever reach. The Hertzsprung-Russell diagram also shows why blue giants are rare. The distribution of stars across the main sequence is not even. The majority of stars, including the countless red dwarfs that dominate the stellar population of galaxies, are located toward the lower right. These stars are faint, cool, and numerous. By contrast, only a small fraction of stars sit in the upper left corner. The diagram therefore provides a clear visual reminder of how exceptional blue giants are in the broader context of stellar populations. Another aspect of their position on the diagram is the shortness of their main sequence phase. The diagram can be thought of as a map of stellar lifetimes. Stars like the Sun remain on the main sequence for billions of years. Stars of much higher mass, however, exhaust their hydrogen fuel rapidly, often in only a few million years. Their path across the diagram is correspondingly swift. After only a short stay in the upper left corner, blue giants begin to shift positions as their cores change composition and their outer layers respond to the new balance of forces. This rapid evolution means that snapshots of clusters containing blue giants often reveal them at different stages, with some still on the main sequence and others already beginning to move away from it. The Hertzsprung-Russell diagram also allows astronomers to study associations between stars. When an entire cluster is plotted, the arrangement of points reveals its age. For young clusters, the most massive stars, including blue giants, remain on the main sequence. For older clusters, those massive stars have already evolved into later stages, leaving only lower mass stars still shining steadily. By comparing the turn-off point of a cluster, which is where stars leave the main sequence, astronomers can determine its age with remarkable accuracy. Blue giants therefore serve as indicators of youth in stellar populations, since their presence signals that a cluster is only a few million years old. Spectroscopy confirms their placement on the diagram. The light from blue giants shows characteristic absorption lines that correspond to ionized elements present at their high surface temperatures. These features distinguish them from cooler stars and reinforce their classification. Observations across multiple wavelengths, including ultraviolet and infrared, provide additional confirmation of their extraordinary luminosity and the heat of their outer layers. The data align with theoretical models that place them firmly in the upper left of the diagram. It is also important to note that the diagram captures not only the present state of a star, but also the trajectory it will follow. Blue giants, while located on the main sequence at first, will not remain there. As their cores evolve, they will begin to move horizontally or vertically across the diagram, tracing paths that eventually lead to supergiants, red giants, or other advanced stages. Their early position in the upper left corner is therefore just the beginning of a path that will unfold quickly, compared with the longer journeys of smaller stars. In the broader context of stellar astrophysics, the Hertzsprung-Russell diagram serves as a unifying framework that connects observations with theory. It provides a way to visualize the life stages of stars in one coherent picture. For blue giants, the diagram emphasizes their distinction from the majority of stars. They are brighter, hotter, and more short-lived. Their rarity is matched by their influence, since their light and energy shape the regions around them. The position of blue giants also underscores the difference between their internal physics and that of smaller stars. The fact that they occupy the upper left corner reflects the dominance of the carbon-nitrogen-oxygen cycle in their cores. This cycle allows them to generate enormous amounts of energy at high temperatures, which in turn sustains their brilliance. Without such a process, their position on the diagram would not be possible. Thus, the diagram is not just a chart of brightness and temperature. It is also a reflection of the underlying nuclear processes that define stellar behavior. In young stellar associations, the presence of several blue giants on the Hertzsprung-Russell diagram provides astronomers with clues about the mass distribution of the cluster. By comparing the observed population with theoretical models, it is possible to reconstruct the initial conditions of star formation in the cloud. This connection between diagram position and birth environment helps researchers understand how galaxies form and evolve. Blue giants, though rare, become critical data points in this analysis. Ultimately, the Hertzsprung-Russell diagram is a tool of clarity. It arranges stars not by arbitrary labels but by measurable quantities, temperature and luminosity. Within this framework, blue giants are unambiguous. They sit high and to the left, standing apart from the majority. This placement captures in one glance what defines them: extreme mass, extreme brightness, and extreme heat, all leading to a short and influential existence. Their place on the diagram is as certain as their rarity. and it serves as the foundation for studying everything else about their nature and their role in the cosmos. The surface temperature of a blue giant is one of its most defining features. While the Sun's surface is around 6,000 degrees Kelvin, the surface of a blue giant can range from 20,000 to more than 40,000 degrees Kelvin. At such high temperatures, the peak of the star's radiation shifts toward the blue and ultraviolet part of the spectrum. This is why these stars appear blue-white to the human eye, and why they dominate the ultraviolet emission of any region where they are present. The link between temperature and color is direct. Hotter stars emit more short-wavelength light, and cooler stars emit more long-wavelength light. The blue giants are at the extreme hot end of this relationship, radiating energy in a way that few other stars can match. Color alone, however, does not tell the full story. Astronomers use spectroscopy to study the detailed properties of stellar light, and the spectra of blue giants are unique. Their high temperatures ionize many elements, stripping electrons away from atoms and leaving behind absorption lines that reveal the presence of ionized helium, oxygen, nitrogen, and other elements. In cooler stars, many of these lines are absent because the temperatures are too low to create them. The appearance of ionized helium, for example, is a signature of O-type stars, which are among the hottest and most massive blue giants. By carefully studying the relative strengths of these lines, astronomers can classify stars into precise spectral subtypes and determine their temperatures with high accuracy. The spectra of blue giants also provide information about their atmospheres. The broadening of spectral lines indicates that their outer layers are subject to strong turbulence and motion, while the presence of certain ionization states confirms the extreme temperatures. In addition, the overall energy distribution of the spectrum allows astronomers to measure luminosity, which when combined with distance estimates confirms that blue giants outshine most other stars by large factors. A single blue giant can emit more light than thousands of suns, flooding its surroundings with radiation that extends deep into the ultraviolet. This radiation affects not only what we observe, but also the environment around the star. Ultraviolet photons have enough energy to ionize hydrogen, and as a result, blue giants often create ionized bubbles of gas around them. These are called H2 regions, and they glow faintly in visible light as electrons recombine with protons and emit photons at characteristic wavelengths, such as the hydrogen alpha line. From Earth, these regions appear as luminous clouds of red or pink light, surrounding clusters of hot stars. The color comes from the specific transitions of hydrogen, but the cause is the intense ultraviolet radiation streaming outward from the hot surfaces of blue giants. Surface temperature also influences the star's stellar winds. The hotter the star, the more intense the outflow of gas driven by radiation pressure. These winds carry away material from the surface and contribute to the overall mass loss of the star. Over millions of years, the total mass lost through winds can significantly alter the star's evolution. Thus, temperature is not just a surface property. It is a key factor in determining the lifetime and final fate of the star. When viewed in clusters, the color differences between stars become striking. The majority of stars appear orange, yellow, or red, reflecting their cooler surface temperatures. Against this backdrop, blue giants stand out vividly. Their intense blue-white glow marks them as the most energetic members of the group. This visual distinction makes them relatively easy to identify even at large distances, and many of the most famous stellar associations visible in the night sky, such as those in the Orion constellation, owe their brightness to the presence of blue giants. The relationship between color and temperature is also supported by theoretical models. According to the laws of blackbody radiation, the spectrum of a star is determined by its surface temperature. The higher the temperature, the shorter the wavelength of peak emission. For blue giants, the peak lies well into the ultraviolet, But because human eyes are sensitive mainly to visible light, the stars appear blue-white. Instruments sensitive to ultraviolet light reveal their full power, showing that the majority of their energy is emitted at wavelengths invisible to us. This explains why regions with blue giants are often bright in ultraviolet surveys, even when they appear only moderately luminous in visible light. Measurements of colour also allow astronomers to estimate interstellar extinction, which is the dimming and reddening of starlight by dust between us and the star. Blue giants with their well-defined intrinsic colours are useful for this purpose. By comparing the observed colour to the expected colour, the amount of reddening can be calculated, providing information about the dust content along the line of sight. This makes blue giants valuable not only for studying themselves, but also for probing the structure and composition of the interstellar medium. The sheer brightness of blue giants sometimes creates observational challenges. Their luminosity can overwhelm nearby fainter stars, making it difficult to analyze clusters in detail. In addition, their ultraviolet output is absorbed strongly by Earth's atmosphere, so observations often require space-based telescopes. Instruments aboard satellites such as the Hubble Space Telescope and the Far Ultraviolet Spectroscopic Explorer have been crucial in studying these wavelengths and in building a complete picture of the emission from hot stars. From a distance, the appearance of a blue giant is that of a point of brilliant light, yet spectroscopy reveals the layers of information encoded within that light. The colour tells us the surface temperature, the spectra reveal the elements and ionization states, and the luminosity confirms the immense energy output. Together, these properties place blue giants firmly in the category of stars that dominate their environments despite their rarity. Their surfaces may seem simple compared with the complexities of their cores, but they provide the most immediate and accessible evidence of the extreme physics taking place inside. In summary, the blue-white colour and high surface temperature of these stars are more than visual characteristics. They are direct consequences of the enormous masses and extreme fusion rates that define blue giants. Their colour signals their heat, their spectra reveal their internal conditions, and their luminosity marks them as among the most powerful stars in the universe. The surface temperature not only determines their appearance, but also sets the stage for the wind's ionization and environmental influence that follow. To observe a blue giant is to see the outward sign of a process that begins deep within the core, where gravity and fusion work together to sustain one of the most remarkable stellar forms known. The luminosity of a blue giant is among its most striking physical properties. Luminosity is the total energy emitted by a star per unit of time across all wavelengths, not just in visible light. For the Sun, this value is steady and modest on a cosmic scale, but for a blue giant, luminosity can exceed the Sun's output by tens of thousands, or even hundreds of thousands of times. This immense energy flow is a natural consequence of the star's high mass, because as mass increases, the central temperature rises, and fusion reactions proceed at much faster rates. The mass-luminosity relationship for stars is not linear. Instead, luminosity grows steeply with mass. A star twice as massive as the Sun is more than twice as luminous, and by the time mass reaches 20 or 30 times solar, the luminosity soars to values that dominate entire regions of space. The radiation released by a blue giant covers a wide spectrum, but the majority lies in the ultraviolet range. Human eyes detect only a fraction of this energy, which is why even the brightest blue giants do not appear overwhelming to observers on Earth. However, when measured with instruments sensitive to ultraviolet light, their true power becomes apparent. The ultraviolet radiation has enough energy to ionize surrounding hydrogen gas, creating H2 regions that extend across many light years. These glowing nebulae are indirect indicators of the massive radiation fields produced by hot stars. In this way, The luminosity of a blue giant not only defines its visibility, but also transforms the interstellar medium around it. The radiation pressure from this luminosity is a defining feature of massive stars. Radiation pressure is the momentum carried by photons as they stream outward from the hot interior towards space. In most stars, radiation pressure contributes modestly to the balance between gravity and outward forces. In blue giants, however, it becomes comparable to gas pressure in the interior, and the outer layers feel a continuous push from the star's light itself. This balance is delicate. Gravity pulls matter inward, trying to compress the star further, while the flood of photons pushes outward. The equilibrium established between these two forces stabilizes the star during its main sequence stage. The impact of luminosity extends beyond stability to mass loss. A star of such brightness constantly drives stellar winds, streams of particles accelerated outward by the force of radiation pressure acting on ions in the atmosphere. These winds strip away significant amounts of material over the star's lifetime. Observations of ultraviolet spectral lines confirm the presence of these winds, showing absorption features that indicate gas moving rapidly away from the star. Typical wind velocities for blue giants can reach thousands of kilometers per second, and the total mass lost can amount to several suns' worth over the course of their short existence. Thus, luminosity is directly linked to the gradual reshaping of the star itself. Astronomers studying clusters and galaxies find that the collective luminosity of blue giants and other massive stars strongly influences galactic ecology. When many such stars form in the same region, their combined radiation can disperse entire molecular clouds, halting star formation locally by sweeping away the raw gas needed to make new stars. At the same time, the radiation enriches the environment by heating and ionizing the gas, producing glowing nebulae visible across great distances. In spiral galaxies, regions of active star formation are often marked by the presence of these bright knots of emission powered largely by the luminosity of young blue giants. The measurement of luminosity requires precise distance estimates. For nearby stars, distances can be determined by parallax, which is the apparent shift in position as Earth moves around the Sun. Once the distance is known, astronomers can convert observed brightness into true luminosity. For blue giants in more distant clusters, methods such as spectroscopic parallax or a main sequence fitting are used. These techniques compare the observed properties of stars with theoretical models to infer luminosity. Regardless of the method, the results consistently show that blue giants are among the brightest stars known, rivaled only by the most extreme supergiants and hypergiants. The energy released by a blue giant each second is so great that it challenges comprehension. If placed at the same distance as the Sun, a typical blue giant would appear hundreds of times brighter, in the sky flooding Earth with levels of radiation that would make life impossible. This is why such stars cannot host habitable planets for long. Their luminosity is simply too intense, and their lifespans too short to provide the stable conditions necessary for life to evolve as it has around the Sun. In this sense, luminosity is not only a defining physical trait, but also a factor that shapes the potential environments of these stars. The study of stellar populations also depends on luminosity. When astronomers observe distant galaxies, they often detect the combined light of many stars. Because blue giants contribute disproportionately to total light despite being rare, they play an outsized role in shaping the appearance of galaxies. A small number of these stars can dominate the spectrum of a young stellar population, adding strong ultraviolet and blue components. This is why galaxies with active star formation often appear bluish, while older galaxies lacking massive stars appear redder. Luminosity therefore connects individual stellar physics with the large-scale appearance of galaxies. The extreme energy output of blue giants also makes them important sources of feedback in cosmological models. Without the radiation and winds from these stars, molecular clouds would collapse into stars more efficiently, and galaxies would look very different. Feedback from luminous stars regulates the pace of star formation and contributes to the cycle of matter within galaxies. When combined with the explosive deaths of massive stars, this feedback seeds the interstellar medium with heavy elements and distributes energy widely. From the perspective of human observation, luminosity makes blue giants valuable markers of cosmic distances. Because their brightness is so great, they can be observed in galaxies millions of light-years away. By comparing observed brightness with expected luminosity, astronomers can estimate distances to those galaxies. Although other methods such as Cepheid variables and supernovae are more precise, blue giants still contribute to distance-scale studies by extending the reach of stellar astrophysics into extragalactic space. In every sense, luminosity defines what a blue giant is and what it does. It is the outward expression of the immense fusion power in the core, the driver of winds that sculpt the star's outer layers, the source of ultraviolet radiation that carves glowing nebulae, and the marker that allows astronomers to detect them across cosmic distances. Without their extraordinary luminosity, blue giants would be less distinctive and less influential. With it, they become dominant players in their environments, shaping not only their own evolution, but also the fate of the regions where they are born. Deep inside, a blue giant energy is generated through nuclear fusion, the process in which hydrogen nuclei combine to form helium. In the Sun and other smaller stars, the dominant pathway is the proton-proton chain, which relies on direct collisions between protons to initiate fusion. In a blue giant, however, the central temperature is so high that another process takes over. This is the carbon-nitrogen-oxygen cycle, which uses these heavier elements as catalysts to accelerate the conversion of hydrogen into helium. Although the end result is the same helium nuclei produced from hydrogen nuclei, with energy released in the form of photons, the path by which it occurs is different and far more efficient at the extreme conditions inside a massive star. The carbon-nitrogen-oxygen cycle begins when a proton collides with a carbon nucleus producing nitrogen. Through a sequence of additional reactions involving oxygen, nitrogen, and more protons, the cycle eventually returns to carbon again, having released a helium nucleus and several energetic particles in the process. The carbon, nitrogen, and oxygen do not disappear. They serve as intermediaries, allowing the process to continue as long as hydrogen fuel remains in the core. Because the probability of these reactions increases sharply with temperature, they dominate over the proton-proton chain in stars hotter than about 15 million degrees Kelvin, a condition easily exceeded within a blue giant. This cycle produces enormous amounts of energy, and the rate of energy production is extremely sensitive to temperature. A slight increase in core temperature can cause a large rise in fusion rate, while a slight decrease can reduce it significantly. This sensitivity makes the balance within the star more delicate than in lower mass stars. In practice, however, the core of a blue giant settles into an equilibrium in which gravity compresses matter inward, while the pressure from fusion-generated energy pushes outward. The two forces cancel each other, allowing the star to maintain stability during its main sequence phase. The structure of a blue giant is shaped by this mode of energy generation. In smaller stars, the core is radiative, meaning energy moves outward, mainly by the diffusion of photons, while the outer layers are convective with heat transported by moving gas. In blue giants, the pattern is reversed. The fusion rate is so rapid in the core that convection dominates there, stirring the central region and mixing hydrogen fuel efficiently. The outer envelope, by contrast, is radiative, allowing photons to stream outward through the atmosphere. This arrangement ensures that fuel is continually brought into the core, prolonging the period during which hydrogen fusion can occur. Without this mixing, the core would exhaust its hydrogen even faster. The intense energy generated in the core begins its journey outward as gamma-ray photons. These photons collide with particles in the dense stellar interior countless times, gradually losing energy and changing wavelength as they scatter. By the time they reach the surface, they have shifted into the visible and ultraviolet range. The outward diffusion of photons can take hundreds of thousands of years, even though the fusion reactions themselves occur instantly on atomic timescales. This slow, outward migration of energy explains why a star's surface brightness remains steady, despite the rapid and continuous activity in the core. Fusion in the carbon-nitrogen-oxygen cycle also produces neutrinos, nearly massless particles that interact only very weakly with matter. Unlike photons, neutrinos escape directly from the core into space, carrying away a small fraction of the star's energy. These neutrinos are difficult to detect, but in principle they provide a direct probe of the nuclear reactions occurring inside massive stars. Neutrino astronomy remains a developing field, yet it offers potential insights into the processes that sustain stars such as blue giants. The rate at which hydrogen is consumed in a blue giant is staggering compared with that of smaller stars. While the Sun has enough hydrogen in its core to fuel stable fusion for around 10 billion years, a blue giant may burn through its supply in only a few million years. This dramatic difference is again a consequence of the steep dependence of the carbon-nitrogen-oxygen cycle on temperature. The more massive the star, the hotter the core and the faster the fuel is consumed. The brilliance of a blue giant is therefore tied directly to the brevity of its stable existence. Observations of young clusters provide confirmation of these theoretical predictions. In such clusters, blue giants are often found alongside smaller stars. By analyzing the spectra and luminosities of the giants, astronomers can determine their masses and fusion rates. The results consistently align with the expectations of the carbon-nitrogen-oxygen cycle as the primary energy source. In addition, models that include convective mixing in the core reproduce the observed lifetimes of blue giants and explain the distribution of stellar types seen in clusters of various ages. The internal structure of blue giants has further implications for their later evolution. Because the core is convective helium produced by fusion, is distributed throughout a larger region rather than confined to a central spot. This means that when hydrogen is exhausted, a relatively large amount of helium is available to contract and heat up, eventually igniting helium fusion. The transition to later stages is therefore smoother than it would be if the core were not mixed. The consequences of this will be felt as the star leaves the main sequence, expands and changes classification, but during the main sequence phase the effect is primarily to extend the period of steady hydrogen burning. Astronomers use both theoretical models and computer simulations to study the behavior of the carbon-nitrogen-oxygen cycle in blue giants. These models include details such as nuclear reaction rates, energy transport mechanisms, and opacity, which is the degree to which stellar material blocks radiation. Comparisons with observations of real stars allow refinements of these models, ensuring that predictions remain accurate. While uncertainties remain in some reaction rates, the overall framework is well established, and the dominance of the carbon-nitrogen-oxygen cycle in massive stars is accepted as a fundamental principle of stellar astrophysics. In essence, the internal fusion processes of blue giants reveal the core reason for their extraordinary properties. Their mass leads to temperatures high enough for the carbon-nitrogen-oxygen cycle to dominate. That cycle produces energy at a rate vastly greater than the proton-proton chain. The energy drives luminosity, surface temperature, and radiation pressure, all of which define what a blue giant is. To understand the bright blue-white glow observed at the surface, one must follow the chain of processes deep into the core where protons combine through the assistance of carbon, nitrogen, and oxygen, generating the energy that sustains one of the most powerful forms of star in the universe. Inside every blue giant, the balance between forces is delicate and continuous. Gravity pulls inward with enormous strength because of the star's mass compressing the gas toward the center. At the same time, radiation pressure and gas pressure push outward, generated by the energy released through nuclear fusion in the core. This balance is what astronomers call hydrostatic equilibrium. In stars like the Sun, gas pressure is the main counterforce to gravity. In blue giants, radiation pressure becomes equally important. Photons streaming outward carry momentum, and when they interact with atoms in the stellar interior, they exert a force that helps to support the star against collapse. Without this outward pressure, the immense gravity of a blue giant would cause it to contract far more quickly. Radiation pressure is a direct consequence of the extreme luminosity of blue giants. The higher the energy output, the stronger the radiation field. Each photon produced in the core eventually migrates outward, colliding with countless particles along the way. Every collision transfers a small push, and the combined effect of countless photons is a measurable outward force. In smaller stars, this contribution is minor, but in blue giants, the density of photons is so high that radiation pressure becomes comparable to or greater than the thermal pressure of gas. This makes massive stars unique in their internal structure and stability. The balance between gravity and radiation is not static. It adjusts as fusion rates vary. If the core temperature rises slightly, the fusion rate in the carbon-nitrogen-oxygen cycle increases sharply. This produces more photons, increasing radiation pressure. The star expands slightly, cooling the core and reducing the fusion rate. If the core temperature falls slightly, fusion slows, radiation pressure decreases, and gravity compresses the core, raising the temperature again. In this way, feedback mechanisms maintain stability despite the extreme sensitivity of fusion rates to temperature. This self-regulation is why blue giants, though unstable in some aspects, can still maintain steady brightness for millions of years. The outward radiation pressure also influences the structure of the outer layers. It creates conditions that allow strong stellar winds to form as particles in the atmosphere absorb and scatter photons. The interaction between radiation and matter in these outer layers is complex. Certain ions, such as those of iron and other metals, absorb ultraviolet photons effectively. Each absorption transfers momentum to the ion, accelerating it outward. This process, called line-driven acceleration, is one of the primary ways blue giants lose mass over time. It is intimately tied to radiation pressure, and without such intense luminosity, the winds would be far weaker. The role of radiation pressure in shaping stellar evolution is profound. It not only balances gravity but also sets a limit on how massive a star can become. If a star exceeds a certain threshold, radiation pressure near its surface can become so strong that it prevents further accretion of material. This theoretical limit is known as the Eddington limit. When the outward force of radiation equals the inward force of gravity acting on a layer of gas, the star cannot grow more massive without losing material. Blue giants approach this limit, and their stability often depends on how closely they balance these opposing forces. Stars much more massive than 100 solar masses are extremely rare, in part because radiation pressure effectively halts their growth. Within the core, convection ensures that hydrogen fuel is stirred and mixed, but radiation dominates the transport of energy through the outer envelope. Photons slowly diffuse outward, taking thousands of years to reach the surface. When they finally emerge, they appear as intense blue and ultraviolet light. The presence of radiation pressure throughout this journey is constant, shaping how the star holds itself together. Even small differences in opacity, which measures how easily photons can move through the gas, can affect the balance. In environments with higher metallicity, the increased opacity enhances the coupling between radiation and matter, strengthening the effect of radiation pressure and winds. Astronomers test models of radiation pressure by comparing predicted mass loss rates with observed spectra. Ultraviolet absorption lines provide evidence of fast-moving winds, while X-ray observations reveal shock fronts within those winds. These observations confirm that radiation pressure is not merely an internal detail, but a force that drives large-scale phenomena visible from light years away. In some cases, variability in brightness and spectral lines suggests that the balance of forces is not perfectly steady. Pulsations and instabilities can occur when the equilibrium is temporarily disrupted, leading to changes in the outflow of material. The influence of radiation pressure extends beyond individual stars to entire star-forming regions. The combined output of several blue giants can carve cavities in molecular clouds, dispersing gas and preventing further collapse. This feedback regulates the number of new stars that form. In this way, radiation pressure from massive stars shapes the structure of galaxies. Without it, the interstellar medium would evolve differently, and the cycle of star formation would proceed in ways that do not match what is observed. At the level of stellar interiors, the balance between radiation pressure and gravity provides a clear illustration of the principles of astrophysics. It shows how forces that seem weak on human scales, such as the momentum carried by light, become dominant when multiplied by the vast number of photons inside a star. It also demonstrates the connection between microscopic processes like photon scattering and macroscopic outcomes like the lifetime and stability of a star. For blue giants, this balance defines their nature and ensures that they shine brilliantly for their brief but influential lives. The story of a blue giant is therefore one of equilibrium maintained under extreme conditions. Gravity tries to compress the star into collapse, while radiation and thermal pressure resist. Fusion in the core constantly replenishes the outward force by generating new photons which slowly make their way outward to the surface. The result is a steady glow visible across great distances, supported by an invisible balance of forces deep inside. This interplay explains not only why blue giants shine so brightly, but also why their existence is short-lived, for the very processes that sustain them also consume their fuel at extraordinary rates. The outer layers of a blue giant are not quiet. From the surface, streams of material flow outward in powerful stellar winds. These winds are continuous outflows of gas, accelerated away from the star by radiation. Unlike the solar wind, which is relatively gentle and slow, the winds of blue giants are strong enough to carry away significant fractions of the star's mass during its lifetime. Observations reveal that these winds can reach speeds of thousands of kilometers per second, fast enough to cross the distance between Earth and the Moon in a matter of minutes. The mechanism driving these winds is tied directly to the star's luminosity. As photons leave the surface, they transfer momentum to ions in the atmosphere. Certain atoms and ions have electronic transitions that absorb photons of specific wavelengths. When a photon is absorbed, its momentum is transferred to the ion, pushing it outward. Because the star produces enormous amounts of ultraviolet light, which is strongly absorbed by many ions, the combined effect is a continuous acceleration of gas away from the star. This is called line-driven acceleration, and it is the defining feature of winds from hot massive stars. The consequences of these winds are far-reaching. Over the course of a few million years, a blue giant can lose several solar masses of material. This mass loss alters the evolution of the star because its later stages depend strongly on how much mass remains in the core and envelope. For some stars, heavy winds strip away the outer hydrogen layers, entirely exposing deeper regions and changing the classification of the star into a Wolf-Rayet star. Even for those that remain as blue giants or evolve into red supergiants, the amount of mass lost through winds plays a decisive role in determining the type of supernova that eventually occurs. Stellar winds also inject energy and matter into the surrounding medium. As gas streams outward, it collides with interstellar material, creating shock fronts that heat the gas to high temperatures. These shocks can produce X-rays detectable by space telescopes. The material carried outward includes not only hydrogen and helium, but also heavier elements synthesized in the core and mixed into the outer layers by convection. This enrichment of the interstellar medium with elements such as carbon, nitrogen, and oxygen contributes to the chemical evolution of galaxies. Later generations of stars form from this enriched gas, incorporating heavier elements into their composition. Thus, the winds of blue giants are one of the ways by which the universe becomes chemically diverse over time. The structure of these winds is not always smooth. Observations show variability in absorption lines, suggesting that the winds are clumpy rather than uniform. This clumping may result from instabilities in the acceleration process. When radiation pushes gas outward, small differences in density can grow into larger fluctuations, producing dense clumps, separated by more rarefied regions. The clumped structure affects how much mass is truly being lost, since measurements assuming smooth winds may overestimate the total rate. Astronomers continue to refine models of wind clumping to better understand the mass loss histories of blue giants. Rotation further complicates the picture. Many blue giants rotate rapidly, sometimes completing a full turn in only a few days. This rapid spin causes the star to bulge at the equator, making it oblate rather than perfectly spherical. The centrifugal force at the equator reduces the effective gravity there, allowing winds to escape more easily. As a result, mass loss can be stronger near the equatorial regions than near the poles. This leads to anisotropic winds in which different latitudes produce different outflow rates. Such asymmetry influences how the surrounding nebulae appear, and may affect the conditions leading up to a supernova. Magnetic fields add another layer of complexity. Although not all blue giants have strong magnetic fields, those that do can channel winds along magnetic lines of force. This creates structured outflows, sometimes forming loops or confined regions of hot plasma. Magnetic confinement can cause the wind to collide with itself, producing shocks and X-ray emission. Measurements of magnetic fields in massive stars are challenging, but where they are detected, they show that magnetism can strongly modify the way winds behave and how mass loss proceeds. The study of stellar winds from blue giants relies heavily on spectroscopy. In the ultraviolet part of the spectrum, strong absorption lines form when outflowing gas absorbs photons from the stellar continuum. The shape of these lines, often with a characteristic P Cygni profile, reveals both the speed and density of the wind. By modelling these profiles, astronomers can measure the velocity structure of the wind and estimate mass loss rates. X-ray observations provide complementary information about the hot shocked gas formed when fast winds collide with slower material or with themselves. Together, these observations build a consistent picture of winds as dynamic, structured, and powerful. The importance of winds extends to binary systems. Many blue giants are members of binary pairs where mass loss from one star can accrete onto a companion. In some systems, this mass transfer leads to dramatic changes in evolution, producing unusual stars or compact objects surrounded by accretion disks. In high-mass X-ray binaries, for example, a blue giant's wind feeds a neutron star or black hole companion, producing intense X-ray emission. These systems are laboratories for studying how winds behave under extreme gravitational influence. From a broader perspective, winds are part of the feedback cycle between stars and their galaxies. They regulate how massive stars evolve, enrich the interstellar medium with heavy elements, inject kinetic energy into surrounding gas, and sometimes feed compact companions. Without winds, the life cycle of matter in galaxies would be very different. The formation of later generations of stars, the appearance of nebulae, and even the balance of star formation rates all depend on the input provided by these powerful outflows. Despite decades of research, many uncertainties remain. The degree of wind clumping the role of rotation and the influence of metallicity on mass loss are still active areas of study. Metallicity is especially important because it determines how effectively ions absorb photons. In galaxies with low metallicity, winds may be weaker, allowing massive stars to retain more of their mass until collapse. In galaxies with higher metallicity, winds strip away more material, altering the population of supernovae and the masses of the remnants left behind. Understanding these dependencies is crucial for building accurate models of stellar evolution across cosmic history. In summary, the stellar winds of blue giants are more than surface phenomena. They are fundamental aspects of what it means to be a massive star. Driven by radiation shaped by rotation and magnetic fields, and influenced by metallicity, they control how much mass a star retains, how it evolves, and how it affects its surroundings. Every photon leaving the surface carries not only energy but also momentum, and together they drive rivers of gas outward into space. These winds are the constant reminder that a blue giant is not a static object, but a dynamic system shedding material and reshaping both itself and the environment throughout its brief lifetime. Rotation plays a powerful role in the lives of blue giants, shaping their structure, their winds, and their eventual fate. Unlike smaller stars, many blue giants spin at extraordinary speeds, completing a full rotation in only a few days. This rapid spin is a natural outcome of their formation. When a large clump of gas collapses into a star, conservation of angular momentum requires that any initial rotation becomes faster as the material contracts. Unless the forming star sheds this spin through interactions with its environment, it can end its birth with significant rotation. In blue giants, the combination of large size and rapid spin produces effects that are visible both at the surface and in the surrounding space. The most immediate effect of rotation is that the star is not perfectly spherical. Centrifugal force pushes outward most strongly at the equator, where rotation is fastest. This reduces the effective gravity there, causing the equator to bulge outward and the poles to flatten. The result is an oblate spheroid, wider at the equator than from pole to pole. Observations confirm this distortion in some massive stars, showing that their diameters vary with latitude. The reduced gravity at the equator also means that surface temperature is not uniform. The poles where gravity is strongest tend to be hotter and brighter, while the equator is cooler and dimmer. This effect, called gravity darkening, alters how the star looks depending on the angle from which it is observed. Rotation also interacts with the star's internal structure. In the core, where fusion proceeds rapidly through the carbon-nitrogen-oxygen cycle, rotation stirs the gas and promotes mixing. This mixing brings fresh hydrogen fuel from outer layers into the core and carries helium and heavier elements outward. By replenishing fuel, rotational mixing can extend the main sequence lifetime of a blue giant, though only slightly compared with its overall brief existence. At the same time, it changes the chemical composition of the surface, making elements like nitrogen more abundant than they would otherwise be. Spectroscopic observations confirm this enrichment, providing evidence that rotation mixes stellar interiors. The role of rotation becomes even more evident in the behavior of stellar winds. Because gravity is weaker at the equator, winds are often stronger, they're producing an asymmetric outflow. In extreme cases, this can lead to disk-like structures of ejected gas concentrated in the equatorial plane. Combined with radiation, pressure rotation enhances mass loss and can alter the angular momentum of the star itself. Over time, winds carry away not only mass, but also rotational energy, gradually slowing the spin. Nevertheless, the influence of rotation during the star's active life is substantial, and it often leaves observable signatures in the shapes of surrounding nebulae. Magnetic fields further complicate the picture. Some blue giants possess strong magnetic fields generated either during formation or by processes in their interiors. When combined with rotation, these fields can channel winds along specific directions, confining them into loops or funnels. The trapped plasma can heat to high temperatures and emit X-rays, while shocks form where streams of gas collide. In magnetic blue giants, the interplay of fields, winds, and rotation produces a structured environment rather than a simple spherical outflow. In binary systems, this structure can influence how material flows toward a companion, altering the behavior of accretion, and leading to variability in the system's brightness. Rotation also introduces instabilities. Rapidly spinning stars can develop oscillations in brightness and surface features that vary over time. Some blue giants are classified as variable stars because their light output changes in ways linked to internal pulsations, often enhanced by rotation. These pulsations provide astronomers with a tool to probe internal structure. By studying the frequencies of variability, researchers can infer conditions inside the star much as seismologists study earthquakes to learn about Earth's interior. Stellar seismology of massive stars remains a developing field, but it promises insights into how rotation affects the distribution of energy and matter within these luminous giants. The extreme case of rotation occurs when a star spins so fast that material at the equator approaches orbital velocity. If the centrifugal force there nearly cancels, gravity gas can be lifted from the surface into space. Such near-critical rotation leads to mass ejection and the formation of circumstellar disks. B-type stars, a class of rapidly rotating B-type stars, show exactly this phenomenon. Although not all B stars are blue giants, the mechanisms at play are similar. In massive stars, such near-critical rotation may play a role in determining whether they eventually collapse into exotic remnants, such as gamma-ray burst progenitors. The rate of rotation also depends on metallicity. In galaxies with low metallicity, stellar winds are weaker, so stars lose less angular momentum during their lives. This allows them to retain faster rotation rates for longer. In higher metallicity galaxies, stronger winds slow stars more effectively. As a result, blue giants in different environments may evolve differently depending on how quickly they spin down. This has implications for the types of supernova they eventually produce and for the characteristics of the compact remnants they leave behind. Observational techniques for measuring rotation rely on spectroscopy. When a star rotates, the light from the approaching limb is slightly blue-shifted, while the light from the receding limb is slightly red-shifted. The combination broadens the spectral lines in a measurable way. By analyzing this line, broadening astronomers can estimate the rotational velocity of the star's surface. For many blue giants, these velocities are hundreds of kilometers per second. This is vastly faster than the Sun's equatorial rotation speed of only about 2 kilometers per second. Such measurements provide direct evidence of the extraordinary rotational dynamics of massive stars. Rotation is not only a property of individual stars, but also an ingredient in broader astrophysical questions. It influences how stars mix their interiors, how they lose mass, how they interact with companions, and how they end their lives. Models of stellar evolution that omit rotation fail to reproduce observed abundances and variability. Only by including rotational effects can theorists match the data gathered from real stars. Thus, rotation is not an optional detail but a fundamental part of understanding blue giants. In summary, the rotation of blue giants shapes nearly every aspect of their existence. It changes their appearance, alters their chemical composition, drives asymmetries in their winds, and influences their long-term evolution. The rapid spin inherited from their birth leaves visible marks on their surfaces, and in their surroundings marks that astronomers detect with careful measurements of spectra and brightness variations. In the life of a massive star, rotation is never just background motion. It is a central feature that guides how the star lives, changes, and eventually dies. The classification of blue giants rests on the careful analysis of their spectra, the detailed fingerprints of light spread out by wavelength. Each star emits a continuous spectrum shaped by its surface temperature, but imprinted upon that spectrum are absorption lines where atoms and ions in the stellar atmosphere absorb specific energies of photons. These lines serve as markers of temperature, pressure, and chemical composition, and they are the foundation of the system used to categorize stars. For blue giants, the relevant categories are O-type stars and early B-type stars, both of which occupy the hot luminous end of the classification scheme. The system of spectral classification begins with letters O, B, A, F, G, K, and M that were originally arranged historically, but are now ordered by decreasing temperature. O-type stars are the hottest, followed by B-type stars. Within each letter, numerical subdivisions further refine the classification. Thus, an O3 star is hotter than an O9 star, and a B0 star is hotter than a B9 star. Blue giants fall within O-type and early B-type, typically with surface temperatures ranging from 20,000 to more than 40,000 degrees Kelvin. Their spectra show features that confirm their high temperatures and distinguish them from cooler stars. In O-type stars, one of the most defining spectral signatures is the presence of ionized helium lines. These appear because the extreme heat strips electrons from helium atoms, allowing transitions that produce distinctive absorption features. As the temperature decreases toward the cooler end of O-type and into early B-type stars, the ionized helium lines fade while neutral helium lines become stronger. At the same time, lines of hydrogen remain prominent across all these stars since hydrogen is abundant and its transitions occur across a wide range of temperatures. By analyzing the relative strengths of hydrogen, helium, and metallic lines, astronomers can place a blue giant into the appropriate spectral subclass. The spectral lines of nitrogen, oxygen, and silicon also serve as indicators. For example, some O-type stars show unusually strong nitrogen lines, evidence of internal mixing that brings nitrogen enriched material to the surface. These variations are not random but connected to rotation mass loss and the internal dynamics of the star. In B-type stars, silicon lines help distinguish subclasses with different ionization states appearing at different temperatures. In all cases, classification depends on matching observed spectra. With standard templates, a process refined over more than a century of stellar astrophysics. Spectral classification not only labels stars but also provides insight into their physical conditions. By combining spectral type with luminosity, class astronomers can determine both temperature and intrinsic brightness. Luminosity class is determined by the width of absorption lines, which depend on surface gravity. Supergiants with low surface gravity produce narrower lines, while dwarfs with higher surface gravity show broader lines. Blue giants generally fall into luminosity classes 3 giants, or as supergiants reflecting their size and brightness. In some cases, stars are classified as a V subgiants if they occupy transitional stages. Together, spectral type and luminosity class provide a two-dimensional framework that locates a star precisely on the Hertzsprung-Russell diagram. The observational importance of blue giant spectra extends beyond classification. Because these stars are so luminous, their light can be studied even at great distances, allowing astronomers to probe the properties of stellar populations in nearby galaxies. By analyzing the integrated spectra of clusters or star-forming regions, astronomers can detect the presence of O-type and B-type stars even when individual stars cannot be resolved. This makes blue giants powerful tracers of recent star formation, since their short lifetimes ensure that any population containing them must be young. Spectral studies also reveal the winds and outflows of blue giants. Many show P Cygni profiles, which are spectral line shapes characterized by absorption on the blue side and emission on the red side. This profile indicates that gases moving outward. Absorption occurs when photons are absorbed by gas flowing toward the observer, while emission arises from gas flowing away and scattering light into the line of sight. By analyzing these profiles, astronomers measure wind speeds and mass loss rates. The presence of such features is one of the hallmarks of hot, massive stars, and it underscores how classification is tied not just to temperature, but also to dynamics. Another aspect revealed by spectra is chemical abundance. Although hydrogen and helium dominate all stars, trace elements leave measurable imprints. In blue giants, surface abundances of nitrogen are often enhanced compared with cosmic averages. This is evidence of rotational mixing, which dredges up processed material from the core to the surface. Variations in surface abundances across populations of blue giants help constrain models of stellar rotation, mixing, and evolution. They also provide information about the chemical history of galaxies, since metallicity influences line strengths and wind efficiency. The precision of spectral classification has improved with modern technology. High-resolution spectrographs allow astronomers to measure line shapes and shifts with remarkable accuracy. These shifts sometimes reveal binary motion, since many blue giants belong to binary or multiple systems. The detection of double-lined spectra in which lines from two stars are visible and shift back and forth allows direct measurement of masses through orbital analysis. In this way, spectroscopy not only classifies stars, but also provides the fundamental parameters needed to test models of stellar structure. The link between spectral features and physical theory is strong. Models of stellar atmospheres predict how radiation passes through layers of hot gas, and these models are matched against observed spectra. Success in reproducing observed line strengths and profiles confirms the accuracy of temperature, pressure, and chemical abundance estimates. Where discrepancies remain, they highlight uncertainties in opacities, wind clumping, or mixing processes. In this sense, spectral classification is both a descriptive system and a test of theoretical astrophysics. Spectral lines also serve as windows into broader astrophysical environments. For example, blue giant spectra sometimes include absorption features not from the star itself, but from interstellar gas along the line of sight. These interstellar lines provide information about the intervening medium, such as its composition and velocity. Thus, studying a blue giant spectrum can simultaneously yield knowledge about the star and about the gas between stars. In conclusion, the classification of blue giants through their spectra is central to our understanding of these massive stars. O-type and early B-type stars are defined by their helium, hydrogen, and metallic lines, and by the combination of spectral type with luminosity class. The system allows astronomers to measure temperatures, luminosities, chemical abundances, and dynamics. It provides a language for describing stars across the universe, and a framework that connects observation with theory. For blue giants, their classification is more than a label. It is a detailed description of their nature drawn directly from the light they emit. Blue giants seldom appear in isolation. More often, they're born within dense stellar nurseries alongside many other stars, and they remain members of clusters or associations throughout their short lives. This is a natural consequence of how massive stars form. Molecular clouds rarely collapse to produce a single star. Instead, they fragment into multiple dense clumps, each of which forms a star or a small system. The regions capable of producing stars massive enough to become blue giants are also the regions most likely to generate many stars at once, resulting in stellar associations where hundreds or even thousands of stars share a common origin. Young open clusters provide some of the clearest examples. In clusters such as the Pleiades or the trapezium in Orion, blue giants dominate the light, even though they are vastly outnumbered by fainter companions. Their intense blue-white glow illuminates the surrounding gas, making these clusters stand out against the background of the galaxy. Observations confirm that the ages of such clusters are only a few million years consistent with the presence of blue giants, since stars of this mass cannot live much longer. Once the giants evolve off the main sequence, the clusters quickly change in appearance, leaving behind primarily smaller stars. The environments of blue giants are shaped by their radiation. The ultraviolet light streaming from their surfaces ionizes nearby hydrogen, producing H2 regions of glowing gas. These regions are often visible in photographs of star-forming complexes as vast diffuse nebulae lit from within. The Orion Nebula, for example, glows largely because of the ultraviolet output of its embedded blue giants. These ionized regions provide a clear marker of recent star formation, and their structure reveals how radiation from massive stars sculpts the surrounding medium. Cavities, pillars, and bright rims all trace the effects of intense stellar light on molecular clouds. Associations of blue giants are sometimes referred to as OB associations, reflecting their spectral types. These are loose groups of O and B-type stars that share a common origin but may not remain gravitationally bound for long. Because their members are so luminous, OB associations can be observed across great distances, even in other galaxies. They serve as signposts of spiral arms and other active star-forming regions. The presence of OB associations also provides evidence for the clustered nature of massive star formation, since such stars almost never appear in complete isolation. The feedback from blue giants extends beyond radiation to include their winds. As multiple massive stars in a cluster shed material at high speed, their winds collide, forming turbulent bubbles of hot gas. These bubbles expand outward, compressing the surrounding medium and sometimes triggering further star formation at their edges. In other cases, the winds disperse the gas, entirely halting further star formation in the immediate vicinity. The balance between these outcomes depends on local conditions, but in both cases the role of the blue giants is decisive. They are engines of change within their clusters, shaping the birth environment of stars around them. Clusters containing blue giants also highlight the role of mass segregation. Over time, the most massive stars tend to sink toward the center of a cluster, while lighter stars drift outward. This process, driven by gravitational interactions, means that blue giants are often found near the cluster core. Their presence there enhances their impact as their radiation, and winds affect the densest regions first. Observations of young clusters confirm this pattern, showing blue giants concentrated in central regions, surrounded by swarms of less massive stars. Another key aspect of cluster environments is the presence of binary and multiple systems. A significant fraction of blue giants are members of binaries, sometimes with companions of comparable mass. In dense clusters, close encounters between stars can alter these systems, leading to exchanges or mergers. Binary interactions can strip outer layers, alter rotation rates, and change evolutionary paths. In fact, some of the most unusual blue giants, such as those showing unexpected chemical abundances or rotational speeds, may be products of binary evolution. Thus, understanding clusters is essential for interpreting the diversity observed among massive stars. The short lifespans of blue giants mean that clusters containing them are temporary stages in galactic evolution. Within a few tens of millions of years, the giants will explode as supernovae dispersing heavy elements into the cluster environment. The shock waves from these explosions can either disrupt the cluster entirely or compress remaining gas to form a new generation of stars. The sequence of formation feedback and disruption creates a cycle that repeats across the galaxy, and clusters of blue giants are among the most active sites in this cycle. In nearby galaxies, associations of blue giants serve as important tracers of recent star formation. Ultraviolet imaging of galaxies such as the Large Magellanic Cloud shows clusters and associations marked by concentrations of O and B-type stars. These observations allow astronomers to reconstruct the star formation history of galaxies, identifying where and when bursts of activity occurred. Because blue giants live for only a few million years, their presence provides a reliable timestamp for the age of their host regions. Even as individual stars, blue giants exert influence far beyond their immediate surroundings. Collectively, in associations and clusters, their impact is multiplied many times. Their combined light winds and eventual supernovae dominate the energy budget of their regions, dwarfing the contributions of the more numerous but smaller stars. The presence of just a few dozen blue giants can transform the appearance and evolution of a cluster, creating glowing nebulae and turbulent bubbles visible across interstellar space. The environments of blue giants remind us that massive stars are not solitary objects but members of dynamic communities. Their births are tied to the collapse of entire molecular clouds. Their lives are lived in the company of thousands of companions, and their deaths reshape the medium from which future stars will form. Associations and clusters are the natural homes of blue giants, and to study these environments is to see the broader context of stellar evolution. In summary, blue giants live not in isolation but in crowded energetic regions where their radiation and winds dominate. They gather in clusters and associations where they light up gas clouds, carve cavities, enrich the interstellar medium, and ultimately end their lives in dramatic explosions that leave lasting marks on their surroundings. Their environments are as much a part of their story as their internal physics for it. It is within these stellar communities that the influence of blue giants is most clearly seen. The powerful radiation of blue giants does not simply shine outward into empty space. It interacts with the surrounding interstellar medium in ways that transform both the star's environment and the cloud from which it was born. The most striking effect is the creation of H2 regions, vast zones of glowing hydrogen gas, ionized by ultraviolet light. These regions form when photons with energies above 13.6 electron volts strike hydrogen atoms, stripping away electrons and leaving behind protons. Once ionized, the hydrogen remains in this state as long as ultraviolet radiation continues to flood the region. When electrons occasionally recombine with protons, they emit photons at characteristic wavelengths, producing the emission lines that give H2 regions their familiar glow. The most prominent of these lines is hydrogen alpha, which lies in the red part of the visible spectrum. This is why many star-forming regions observed in photographs show a reddish-pink colour surrounding clusters of blue giants. The structure of an H2 region depends on the balance between ionizing radiation and the density of surrounding gas. Close to the star, nearly all hydrogen is ionized. Farther out, the radiation weakens as photons are absorbed, and a sharp boundary forms where neutral hydrogen dominates again. This boundary, called the ionization front, can be observed as a bright rim or edge in nebulae. The shape of the ionization front is often irregular because molecular clouds are clumpy, with dense knots of gas resisting ionization longer than diffuse regions. The result is a sculpted environment of pillars, cavities, and filaments shaped by the interplay between starlight and gas. The Orion Nebula provides one of the clearest nearby examples. At its heart lie several blue giants in the trapezium cluster. Their ultraviolet light ionizes the surrounding gas, creating a bright H2 region, visible even to small telescopes. The glowing gas outlines the effect of the radiation, while dark lanes of dust show where ionization has not penetrated. This kind of environment illustrates how blue giants act as engines of feedback, reshaping their surroundings on scales far larger than the stars themselves. The energy deposited into the gas does more than produce light. It heats the ionized material to temperatures of about 10,000 degrees Kelvin, raising its pressure compared with the cooler neutral gas nearby. This pressure difference drives expansion, pushing the ionized region outward into the molecular cloud. As the ionization front advances, it can compress dense clumps of gas, sometimes triggering new episodes of star formation at the edges of H2 regions. In this way, the presence of blue giants can both inhibit and promote star formation. They destroy parts of the cloud by dispersing gas, yet they can also seed the conditions for new stars to emerge in compressed regions. Observations of giant star-forming complexes in our galaxy and others show these processes clearly. The Eagle Nebula, with its iconic pillars of creation, reveals dense fingers of gas being eroded by radiation from nearby blue giants. At the same time, the tips of the pillars harbour embryonic stars formed under the pressure of advancing ionization fronts. Similar structures are observed in the Carina Nebula, where clusters of massive stars illuminate vast expanses of gas, carving intricate patterns in the interstellar medium. In every case, the presence of blue giants is the driving factor behind the visible forms of the nebulae. The feedback from ionizing radiation also has implications for galaxy evolution. In regions where many blue giants form together, the combined ultraviolet output creates superbubbles of ionized gas that can span hundreds of light years. These superbubbles can merge with one another, creating channels through which hot gas escapes into the galactic halo. In extreme cases, this process contributes to galactic winds that carry energy and material far from star-forming regions. Thus, the radiation from blue giants plays a role not only on local scales, but also on the broader ecology of galaxies. Astronomers study H2 regions using spectroscopy to measure the emission lines produced by recombining hydrogen and by other ionized elements such as oxygen, nitrogen, and sulfur. These lines reveal the temperature, density, and chemical composition of the gas. By comparing observed line strengths with models, researchers can infer the rate of ionizing photons emitted by the stars, and thus confirm the presence of blue giants even when the stars themselves are obscured by dust. In this way, H2's regions serve as indirect indicators of massive stars in both our galaxy and distant galaxies. The influence of radiation extends beyond hydrogen. The same ultraviolet photons that ionize hydrogen also ionize helium and heavier elements. This produces emission lines that provide further information about the radiation field and the abundances of elements in the interstellar medium. In metal-rich environments where elements heavier than helium are more abundant, the emission spectra are more complex, reflecting the stronger absorption of radiation by these atoms. In metal-poor galaxies, the spectra are simpler, but the radiation penetrates farther, altering the balance of star formation in those systems. The interaction of radiation with dust grains adds another dimension. Dust absorbs ultraviolet light and re-emits it in the infrared. Observations of star-forming regions in infrared wavelengths reveal the warm glow of dust heated by blue giants. This reprocessed radiation can escape more easily than ultraviolet, providing a way for astronomers to detect the hidden energy output of massive stars even when they are deeply embedded in their natal clouds. infrared astronomy has shown that many of the most active star-forming regions in the universe are powered by clusters rich in blue giants whose direct light is obscured. The presence of H2 regions is also tied to timescales. Because blue giants live only a few million years, H2 regions cannot persist longer than that. Once the stars die, the supply of ionizing photons ends, and the gas quickly recombines to become neutral again. This makes H2 regions temporary structures existing only during the brief lifetimes of their massive progenitors. Their presence in a galaxy signals ongoing star formation, while their absence in older regions confirms that massive stars have already evolved away. In summary, the ultraviolet radiation of blue giants transforms surrounding hydrogen into glowing ionized regions, creates expanding bubbles of hot gas, sculpts the shapes of molecular clouds, and influences the birth of new stars. These processes are visible in some of the most iconic nebulae of the night sky, and extend their influence to the broader dynamics of galaxies. The interaction between blue giants and the interstellar medium demonstrates that stars are not isolated points of light, but active participants in shaping the environments in which they live. As a blue giant ages, the delicate balance of forces in its core begins to shift. During the main sequence phase, hydrogen fusion through the carbon-nitrogen-oxygen cycle provides the outward pressure needed to counteract gravity. Over time, however, the hydrogen in the core becomes depleted. Helium accumulates, and because helium nuclei cannot fuse at the same temperature as hydrogen, the fusion rate in the very center declines. Without steady energy generation at the exact core, gravity begins to compress it more tightly. The rising density and temperature eventually ignite hydrogen fusion in a surrounding shell, while the inner helium-rich core continues to contract. This structural change marks the first step in the evolution of a blue giant away from the main sequence. The star's outer layers respond to these internal changes. As the core contracts and the shell burns, energy output increases. The envelope expands and cools, shifting the star's surface temperature downward. On the Hertzsprung-Russell diagram, the star moves away from the upper left corner, where hot main sequence stars lie, and begins to trace a path toward cooler and more luminous regions. Depending on its mass, the star may swell into a blue supergiant, a luminous blue variable, or transition further into a red supergiant. The trajectory depends on mass metallicity and the degree of mass lost through winds earlier in its life. The ignition of helium fusion is the next major milestone. When the contracting helium core reaches a temperature of about 100 million degrees Kelvin, helium nuclei begin to fuse into carbon and oxygen through the triple alpha process. This new source of energy halts the core's contraction for a time and establishes a new equilibrium. Because the fusion of helium releases less energy per reaction than the fusion of hydrogen, the rate of consumption is still rapid compared with smaller stars. The star continues to evolve on million-year timescales far shorter than the billion-year timescales of solar-like stars. Throughout this process, the outer appearance of the star changes dramatically. Some blue giants maintain high surface temperatures and become classified as blue supergiants. Others expand further and cool significantly, becoming red supergiants with enormous radii. Betelgeuse in Orion is a well-known example of such an evolved massive star, although it likely did not begin as one of the most extreme blue giants. More massive stars can cycle between phases, moving back and forth across the diagram as they undergo successive stages of nuclear burning and as mass loss alters their structure. Variability often accompanies these transitions. As the balance between core contraction and envelope expansion shifts instabilities, can cause fluctuations in brightness and spectral features. Some blue supergiants are observed as variable stars with light output that changes over days, months, or years. These variations provide clues to internal processes since pulsations can carry information about density and temperature structure. In some cases, variability signals dramatic changes, as in luminous blue variables that undergo sudden eruptions and expel large amounts of mass. Such stars are rare but demonstrate the extreme instability that can accompany advanced stages of massive star evolution. Rotation and winds continue to play roles during this phase. As the envelope expands, rotation slows, but the earlier mixing it caused can affect how quickly the star evolves. Winds remain powerful, carrying away mass and altering the ratio of core to envelope. In some stars, winds strip the outer hydrogen layers entirely, leaving behind bare helium cores visible as Wolf-Rayet stars. These stripped stars shine with even higher temperatures and reveal strong emission lines in their spectra, marking another possible evolutionary pathway from blue giants. The exact path a blue giant takes depends strongly on metallicity. In galaxies with high metallicity, winds are stronger and mass loss is greater. This favors the removal of outer layers and the appearance of Wolf-Rayet stars. In metal-poor galaxies, winds are weaker, allowing stars to retain more mass and remain in different evolutionary states longer. These differences influence the types of supernovae observed in different galaxies, since the final structure of a massive star at collapse determines the nature of the explosion. Computer models trace the internal changes through successive burning stages. After helium is exhausted in the core, carbon fusion begins, followed by oxygen, neon, and silicon. Each stage proceeds more rapidly than the last, with timescales shrinking from thousands of years to only days. The end result is the buildup of an iron core which cannot generate energy through fusion. At that point, no outward force can resist gravity, and collapse becomes inevitable. But long before that terminal stage, the star has already transformed itself many times, shifting classification and altering its visible characteristics. Astronomers observe these evolutionary changes most clearly by studying clusters that contain multiple blue giants. Because all stars in a cluster share the same age, the range of stellar types present reflects the range of masses. The most massive stars evolve fastest, moving off the main sequence first. By comparing the positions of stars on the Hertzsprung-Russell diagram, astronomers can identify which are still hydrogen-burning blue giants, which have become blue supergiants, and which have shifted further into cooler expanded phases. These observations provide tests of theoretical models confirming the rapid and complex evolution of massive stars. The evolution of a blue giant is thus a process of continual adjustment. As the core fuel changes, the structure readjusts, leading to shifts in luminosity, temperature, and radius. The surface appearance may move from blue to red or may cycle between states. Instabilities may arise, leading to variability or eruptions. Mass loss continually reshapes the star, influencing what remains when collapse finally comes. Although the broad outline of these stages is well understood, details remain uncertain, especially the exact rates of mass loss and the role of rotation and binarity in altering evolutionary tracks. In essence, the path of a blue giant after hydrogen exhaustion is one of transformation. It leaves the main sequence, becomes larger and more luminous, ignites new fuels in its core, and changes classification. The details of the journey vary with environment and initial conditions, but the pattern of rapid evolution is universal. The brief, brilliant main sequence life of a blue giant is only the beginning of a sequence of changes that unfold swiftly, by cosmic standards leading inexorably toward the end of nuclear fuel and the collapse that follows. The end stages of blue giants are shaped by the same factor that defined their birth, their immense mass. While smaller stars like the Sun eventually become white dwarfs after gently shedding their outer layers, the fate of a blue giant is far more violent. Once hydrogen fusion in the core has ended and successive stages of helium-carbon and heavier element burning take place, the star marches quickly toward a final outcome. Each new stage of fusion proceeds faster than the one before. Helium burning can last hundreds of thousands of years, carbon burning only a few hundred years, and silicon burning less than a single day. These timescales illustrate how rapidly energy demands rise as the star nears its final state. At the center, fusion ultimately produces iron. Unlike lighter elements, iron cannot release energy through fusion because its nucleus is already at the point of maximum binding energy. Attempts to fuse iron require more energy than they release, and so when an iron core builds up, the central engine of fusion that sustains the star shuts down. With no new outward pressure to balance gravity, the iron core grows unstable. Once it reaches a critical mass known as the Chandrasekhar limit of about 1.4 solar masses, it can no longer resist collapse. The collapse is catastrophic in speed and scale. The core implodes in less than a second, driving densities to extreme levels. Electrons and protons combine to form neutrons, releasing a flood of neutrinos. The outer layers of the star, no longer supported, fall inward toward the collapsing core. When they strike the stiffening neutron-rich matter, the infalling material rebounds, and combined with the energy from neutrino outflow, this rebound drives a shock wave outward. The result is a core collapse supernova, one of the most energetic events in the universe. From an external perspective, the death of a blue giant is sudden. Within hours, its brightness can increase by factors of millions, briefly outshining the entire host galaxy. The ejected material expands outward at thousands of kilometers per second, spreading the heavy elements forged inside the star into the interstellar medium. These include not only carbon, nitrogen, and oxygen, but also elements such as silicon, sulfur, and calcium. In the aftermath, enrichment continues as supernova nucleosynthesis produces even heavier elements. The debris eventually mixes with interstellar gas, contributing to the chemical diversity of future generations of stars and planets. The core left behind after collapse depends on the mass of the progenitor. For many blue giants, the collapsed core stabilizes as a neutron star, an object so dense that a teaspoon of its matter would weigh billions of tons on Earth. Neutron stars spin rapidly and can generate strong magnetic fields, sometimes becoming pulsars that beam radiation in regular pulses. In cases where the progenitor star was even more massive, the collapse continues beyond the neutron star stage to form a black hole. The exact dividing line between neutron star and black hole outcomes depends on uncertain factors such as rotation mass loss and binary interactions. The diversity of supernovae observed reflects these differences. Type II supernovae occur when hydrogen-rich outer layers remain intact, producing characteristic hydrogen lines in their spectra. If winds or binary interactions have stripped away the hydrogen, the explosion appears as a type I Borisy supernova, distinguished by the absence of hydrogen lines, and in the case of type I, also helium. These classifications connect directly to the life histories of blue giants and the degree of mass loss they experience before collapse. In some cases, blue giants end their lives in even more extreme explosions. Very massive stars can undergo pair instability supernovae, where high-energy gamma rays in the core create electron-positron pairs, reducing pressure and triggering collapse. If conditions are right, the collapse reverses explosively and disrupts the star completely, leaving no remnant. These events are rare and depend on both mass and metallicity, but they represent another possible fate for the most massive blue giants. The short lives of blue giants mean that their supernovae occur soon after the star-forming event that created them. In young clusters, it is common to find both newborn stars and the remnants of recent supernova within a few million years of one another. This rapid turnover contributes to the cycle of star formation and feedback in galaxies. The shock waves from supernovae compress nearby gas, potentially triggering new star formation, while also dispersing and heating the surrounding medium. In this way, the death of a blue giant feeds directly into the birth of future stars. Supernova remnants provide evidence of these processes. Expanding shells of gas such as the Crab Nebula or Cassiopeia display the material ejected by massive stars. Within these remnants, astronomers detect signatures of heavy elements that match theoretical predictions of nucleosynthesis. The remnants also reveal the energy deposited into the interstellar medium as shock-heated gas emits in radio X-ray and optical wavelengths. Observations of such remnants confirm the essential role of blue giants in enriching and energizing galaxies. Astronomers study supernovae from blue giants not only to understand stellar evolution, but also because they serve as tools for probing the universe. Supernovae can be observed across great distances, allowing astronomers to measure the rates of star formation in distant galaxies. The light curves and spectra of core-collapse supernovae reveal both the properties of the exploding star and the conditions of its environment. They also provide laboratories for extreme physics, since the densities and energies involved cannot be reproduced on Earth. Despite these advances, uncertainties remain. The exact mechanisms that allow the collapsing core to drive an outward explosion are still the subject of intense research. The role of neutrinos' convection and rotation in reviving the shock wave is complex and modelled with sophisticated simulations. Similarly, the influence of binary interactions in shaping final outcomes is an active area of study. Some blue giants may merge with companions or transfer mass in ways that alter their evolution dramatically, leading to outcomes different from those predicted for single stars. In summary, the endpoints of blue giants are supernovae and compact remnants. Their massive cores collapse when iron halts fusion, their outer layers are blasted into space, and the remains form neutron stars or black holes. Along the way, they enrich galaxies with heavy elements and drive the dynamics of the interstellar medium. The violent deaths of blue giants contrast with the quiet fading of smaller stars, yet both processes are essential for the cosmic cycle of matter. In the brief span of a few million years, a blue giant passes from formation to explosion, leaving behind both remnants and enrichment that shape the future of the universe. Even though astronomers understand the broad outlines of how blue giants form, live and die, many details remain uncertain, and these uncertainties are the focus of ongoing research. One of the most challenging questions concerns the true rates of mass loss through stellar winds. Observations clearly show that blue giants shed large amounts of material over their lifetimes, but the exact quantities are difficult to measure because winds are clumpy rather than smooth. If the wind is assumed to be uniform, mass loss rates can be overestimated by factors of several. If the clumping is accounted for, the rates appear lower, but by how much is still debated. This uncertainty matters because the amount of mass loss determines what kind of supernova the star will produce, and whether it will end as a neutron star or a black hole. Another area of uncertainty involves rotation. Models of stellar evolution that ignore rotation cannot explain the observed surface abundances of elements such as nitrogen in many blue giants. Rotational mixing brings nuclear-processed material from the core to the surface, changing the chemical fingerprint seen in spectra. However, the efficiency of this mixing depends on poorly constrained factors such as internal angular momentum transport turbulence and magnetic fields. Some blue giants rotate extremely fast, while others of similar mass rotate more slowly. The reasons for this diversity are not fully clear. Binary interactions may play a role since stars in close pairs can exchange angular momentum during mass transfer or mergers, but single-star mechanisms must also be important. Magnetic fields add further complexity. A fraction of blue giants exhibit strong surface magnetic fields, while others appear to have none detectable. When present, these fields can channel stellar winds, confine plasma, and even slow rotation by exerting magnetic braking. Yet the origin of these fields is still debated. Some may be remnants of the star-forming process, while others may be generated by internal dynamos. The difference between magnetic and non-magnetic blue giants leads to very different evolutionary paths, and until the origin and frequency of magnetic fields are understood, predictions about their outcomes remain uncertain. Metallicity, the proportion of elements heavier than hydrogen and helium, also influences blue giant evolution, and it varies across galaxies. In the Milky Way, where metallicity is moderate, winds are strong and strip away significant mass. In dwarf galaxies with low metallicity, winds are weaker, allowing stars to retain more mass and collapse into heavier remnants. This dependence explains why black holes detected by gravitational wave observatories, which often have masses much higher than expected for black holes formed in our galaxy, may have originated in low metallicity environments. Yet the precise scaling of wind strength with metallicity is still under study, and small uncertainties can produce large differences in predicted outcomes. Binarity introduces one of the largest sources of uncertainty. Surveys show that a majority of massive stars are part of binary or multiple systems. Interactions between companions can strip away outer layers, alter rotation, or even cause two stars to merge. These processes produce outcomes very different from those of isolated stars. Some blue giants may gain mass from a companion and extend their lifetimes, while others may lose so much mass that they evolve into unusual stripped envelope stars. Binary evolution is also thought to play a role in producing long gamma-ray bursts, one of the most energetic phenomena in the universe. Yet because binary interactions are complex and varied, including cases of common envelopes and mergers predicting their influence, remains one of the most active fields in stellar astrophysics. Variability is another phenomenon that highlights uncertainty. Some blue giants are observed to pulsate changing brightness over regular intervals. Others exhibit irregular variability tied to instabilities in their outer layers or eruptions of mass. Luminous blue variables are a particularly enigmatic class, undergoing episodes of dramatic outbursts that can rival supernovae in brightness, but do not destroy the star. Famous examples such as Eta Carinae demonstrate how unpredictable massive stars can be in advanced stages of evolution. The triggers of these outbursts remain uncertain, though they are likely related to instabilities near the Eddington limit, where radiation pressure nearly equals gravity. Understanding these processes requires both detailed observations and advanced simulations that capture the interplay of radiation, convection, and rotation. The endpoints of blue giants also remain an open question in many cases. While some collapse to form neutron stars and others to black holes, the dividing line is not sharply defined. Factors such as mass loss rotation and binarity all shift the boundary. Some models suggest that certain stars collapse directly into black holes without a visible supernova, a scenario sometimes called a failed supernova. Observational evidence for disappearing stars in nearby galaxies supports this idea, but the frequency of such events is unknown. Clarifying how often blue giants collapse quietly compared with how often they explode is a major challenge for future observations. The role of blue giants in shaping galaxies extends the uncertainties even further. Their radiation winds and explosions provide feedback that regulates star formation, but the details of how this feedback operates are complex. In some regions, feedback triggers new star formation by compressing gas, while in others it suppresses it by dispersing clouds. The balance depends on density, turbulence, magnetic fields, and clustering. Simulations of galaxy evolution must include these processes, but because they are difficult to model accurately, uncertainties in blue giant behavior propagate upward to uncertainties in galactic scale predictions. Even with these unknowns, the study of blue giants continues to advance rapidly. Instruments capable of high-resolution spectroscopy reveal details of winds and surface abundances. Space-based observatories detect ultraviolet radiation and X-rays that trace hot plasma and shocks. Interferometric techniques allow astronomers to resolve the shapes of nearby blue giants, confirming their oblateness and surface variations due to rotation. Gravitational wave detections of black hole mergers provide indirect evidence of massive star evolution in environments far from our own. Each new observation helps narrow the uncertainties and refine the models. In this sense, blue giants are not only subjects of study, but also tools for exploring astrophysical processes. Their winds probe the physics of radiation-matter interactions. Their rotation and mixing test theories of angular momentum transport. Their variability offers a window into instabilities near the limits of radiation pressure. Their death seed galaxies with heavy elements and power some of the most luminous transients in the universe. The questions that remain about them are not gaps, but opportunities pointing to directions where understanding can deepen. In conclusion, while the overall narrative of blue giants is clear, they form from massive clouds, live short and luminous lives and end in collapse. The details remain rich with uncertainty. Mass loss rotation, magnetic fields, metallicity, binarity, variability, and endpoints all introduce complexities that continue to challenge astronomers. These open questions ensure that blue giants remain central not only to the story of stellar evolution, but also to the continuing development of astrophysics itself. The uncertainties are not limitations, but signals that there is more to learn, and that each blue giant observed is a chance to refine what is known about the most massive and luminous stars in the cosmos.